Welcome to this walkthrough on unsupervised anomaly detection using a variational autoencoder, or VAE. Today, we'll be working with the credit card fraud detection dataset from Hugging Face, and we'll show you how to train a neural network that learns to identify fraud, without being explicitly told what fraud looks like. Let's dive into each step. We begin by installing essential Python libraries, datasets for accessing Hugging Face datasets, Torch for building deep learning models, and scikit-learn and matplotlib for preprocessing and visualizations. These tools form the foundation of our pipeline. Next, we import all necessary modules. We also set our key configuration values, such as batch size, training epochs, latent space dimension, and the KL divergence scaling factor beta. These hyperparameters will influence how well our VAE generalizes normal behavior. Here, we load the dataset davidEGS/credit card fraud detection from Hugging Face. We convert the Hugging Face dataset into a pandas data frame, and separate features from the target label, class. We split the data into training and test sets, using stratified sampling to preserve the rare fraud-to-normal ratio. Importantly, we train our model only on normal transactions. This simulates a real-world scenario where fraudulent examples are rare and typically unknown during training. We standardize the features using standard scalar, and finally convert everything into PyTorch tensors. Now we define our model, a VAE designed for tabular anomaly detection. The encoder has two paths, one for PCA transformed features, and one for raw values like time and amount. The outputs are the mean and log variance vectors used to sample a latent vector. The decoder reconstructs the input from this latent space. This architecture allows the model to compress and reconstruct normal transactions while learning a distribution of their underlying patterns. In this section, we loop through the training data for 50 epochs. For each batch, we compute the weighted reconstruction loss and KL divergence. The KL divergence pushes the latent space to resemble a normal distribution, improving generalization. We then combine both losses, backpropagate the error, and update the model. Throughout training, the model becomes better at reconstructing only normal patterns, meaning that fraud will reconstruct poorly, resulting in a higher error. Once trained, we pass the full test set through the model and compute the weighted reconstruction error for each sample. This becomes our anomaly score. We calculate the ROC-AUC and plot a precision recall curve. We also compute the F1 optimal threshold, which gives us the best balance between detecting fraud and avoiding false positives. We then visualize the model's performance using a precision recall curve. This helps us understand the trade-off between precision and recall at different thresholds, which is especially important in imbalanced datasets like fraud detection. Now we define two helper functions. is_fraud classifies a single transaction based on its reconstruction error. top_k_anomalies ranks and returns the top anomalies in the dataset. We demonstrate this by printing out the first fraud instance and the top 10 highest error transactions, which typically include multiple frauds. Finally, we use Seaborn to plot the distribution of reconstruction errors for both normal and fraudulent transactions. We also overlay our optimal threshold. The plot clearly shows the model's separation power. Normal samples cluster around low error, while fraudulent ones stretch into a heavy tail with much higher reconstruction error. In summary, this complete implementation builds and trains a variational autoencoder on normal transactions, then scores and identifies frauds using reconstruction error. You now have a clean, production-grade anomaly detection system that can be tuned to meet real-world business requirements, whether that's high recall, high precision, or a balance of both. If you found this helpful, don't forget to share or subscribe. Until next time, keep experimenting and keep improving.